It's only 4.2 light-years away, and yet it seems virtually inconceivable that we will ever reach Proxima b. This is all the more regrettable, given that the celestial body is not only the closest exoplanet to Earth, but is also suspected of being habitable. Given that we are not even succeeding in conquering the planetary world right on our doorstep, one might think that interstellar travel in general will remain an unfulfilled dream forever. But it doesn't have to be that way. In fact, experts are currently working hard on the development of new propulsion systems that will soon enable us to leap to the stars and finally bring exoplanets like Proxima b within our reach. But what groundbreaking concepts are being discussed in this regard? How realistic is their implementation, and could Proxima b actually become our interstellar springboard? If anyone knows how to explore the vastness of space, it's the two Voyager probes. No wonder, because Voyager 1 and 2 have now covered incredible distances of 24.67 and 20.62 billion kilometers between them and the Sun. This in turn corresponds to 165 and 138 astronomical units, and thus not even a single light day. This is estimated at around 173 astronomical units, and if we now consider that Proxima b is about 4.2 light-years away from us, we realize that the Voyager probes would have to fly another 70,000 years before they would reach our planetary neighbor. And at this point, it should be noted that the identical sister probes are by no means chugging through space at a leisurely walking pace, but are sweeping through interstellar space at around 61,000 kilometers per hour. Despite all this, the title for the fastest man-made object of all time does not go to Voyager, but to the Parker Solar Probe, which was launched in 2018 and reached a mind-boggling speed of more than 635,000 kilometers per hour in July of this year. And yet, even this artificial Speedy Gonzales would need several millennia before it would arrive at the Proxima Centauri system. And as we now know, the eponymous red dwarf in the Centaurus constellation does not travel through the universe alone. On the one hand, Proxima Centauri is part of a triple star system, which is completed by Alpha Centauri A and Alpha Centauri B. On the other hand, it also represents the central star of a planetary system that has at least 3 members. And in particular, it's Proxima b, discovered in 2016, that repeatedly attracts astronomical interest. And that is not particularly surprising. After all, we are dealing here with a rocky planet within the habitable zone that achieves a remarkable value of 0.87 on the Earth Similarity Index. A brief explanation. The habitable zone corresponds to the distance range within which a planet must be located in relation to its host star for water to be able to exist there in a permanently liquid form. The Earth Similarity Index indicates how much an exoplanet resembles our earthly home in terms of energy flow, mass, and radius. But does this now mean that Proxima b embodies a cosmic twin of the Earth? Is Proxima b Earth 2.0? Well, not necessarily, but one thing at a time. Proxima b, with a mass of 1.17 Earth masses, is generally classified as an Earth-like exoplanet. But be careful. The term Earth-like refers only to rocky planets with solid surfaces, without providing any information about their habitability. And while Earth is known to take 365 days to orbit the Sun, Proxima b only needs a little over 11 days for one orbit. This is for the simple reason that the distance between the exoplanet and its host star is just 7 million kilometers. But that's not all. In fact, there is growing evidence that Proxima b has a tidally locked rotation, which means that it always presents the same side to its host star. Consequently, its surface is also divided into a bitterly cold night side and a significantly hotter day side. And yet, there would be a narrow strip between these two extreme zones that allows life to flourish. But according to our current knowledge, water is also needed for that development. And lo and behold, assuming the appropriate orbital parameters and suitable atmospheric composition, the expert simulations have shown that the cool wet stuff could actually be splashing around here in abundance. However, it should be noted at this point that we are dealing with a purely theoretical model, because in reality, Many parameters that would be necessary for the existence of liquid water have not yet been conclusively investigated. And then there is also the problem of radiation. Although Proxima Centauri, a red dwarf, only has about 12% of the mass of the Sun, it attracted attention a few years ago with an unprecedented radiation burst. In detail, researchers at the University of Colorado observed how the star increased its ultraviolet radiation 14,000-fold within a few seconds. The monster eruption was thus even 100 times stronger than any solar flare recorded to date. And then, there is also the fact that the eruptions on Proxima Centauri are not only significantly more intense, but also much more numerous than in our home system. In view of this, the gloomy forecasts predict that the extreme radiation from the host star will sooner or later destroy the entire atmosphere of Proxima b and put an end to the development of life once and for all. And yet, there is a scenario in which the exoplanet can withstand the turbulent radiation bursts of its host star. To do this, it needs a liquid core that forms a stable magnetic field that blocks the radiation and prevents the oxygen and water molecules from escaping into space. Furthermore, it's conceivable that Proxima b is still drawing from its original water reservoir. One theory is based on the assumption that the planet actually originated at a much greater distance from its host star and was only later captured by it. Some simulations have shown that there was once 10 times more water on Proxima b than on Earth. And even if it had already lost 90% of its water due to the extreme stellar radiation, there would still be enough today for a gigantic ocean covering a large part of the planet's surface. However, due to the natural subdivision, the water could only be present in a permanently liquid form in the narrow twilight zone. On the day side, it would be more like a seething pot, while on the night side, it would freeze to ice. The dream of interstellar travel. Will we ever reach Proxima b? The two Voyager probes are powered by radioisotope thermoelectric generators, which convert the heat from the radioactive decay of plutonium into energy. However, as already mentioned, it would take the two most remote outposts of humanity tens of thousands of years to reach the Proxima Centauri system. So what do you do when the outdated propulsion technologies have had their day? That's right, you switch to good old sailing. Yeah, you heard right. Because what may sound like a rather dusty idea at first is in fact the core of the revolutionary Breakthrough Starshot research project. And while its financier and internet billionaire Yuri Milner is not exactly one of the most famous faces in astronomical research, renowned experts such as Stephen Hawking, Avi Loeb, and Freeman Dyson have also participated in the endeavor, which began in 2016. In a nutshell, Breakthrough Starshot aims to prove that it's not only possible, but above all, realistic to send a spacecraft to the realms of Proxima Centauri, and in just 20 years, no less. But how is that even possible? How can the predicted travel time of around 70,000 years be reduced to this almost ridiculously short period of time? Well, basically, where ambitions are great, you sometimes have to take smaller steps to achieve them. Specifically, the initiative aims to launch nanoprobes weighing just a few grams into orbit, whose solar sails will then be illuminated by a powerful laser from Earth. Subsequently, the light pressure is to accelerate the mini-probes to 20% of the speed of light within a very short time, thus enabling them to achieve the eponymous Starshot breakthrough. How a mini spaceship could travel to Proxima b. Incidentally, the idea of propelling a spaceship equipped with light sails in this way is not new. In fact, the American physicist Robert Forward had already proposed it in the 1970s, and yet, this particular propulsion concept has some special requirements. In order to achieve the required speed of 60,000 kilometers per second and to be able to withstand the acceleration of several 10,000 grams, the dimensions of the components must be reduced to an absolute minimum. More specifically, Breakthrough Starshot envisions the development of a miniature spaceship the size of a microchip. This would consist of nothing more than a coded control computer, a power source, a camera, a receiver, a transmitter, and a solar sail. However, Merely producing this technical midget is not enough on its own. As mentioned, it also requires an Earth-based laser thrust. In detail, however, it would require not just one, but a multitude of lasers that combine to form a 100 gigawatt beam and that target the 4 by 4 meter area of the solar sail 20 million kilometers away during the acceleration phase. If this is successful, a laser beam of just 10 minutes should be able to pave the way for the nanoprobe to Proxima Centauri. But doesn't this all sound somehow utopian? After all, the tiny spaceship would then somehow have to manage to decelerate at the destination in time. Expressed in figures, the probe would have to decelerate from 20 to around 4.6% of the speed of light in order to avoid rushing past the star system of desire within a few seconds. Now, in this regard, some researchers point out that it might be better to abandon the concept of a huge energy-guzzling laser anyway and use solar radiation instead. In this case, however, it would need a sail about 100,000 square meters in size, made of a light yet robust material such as graphene. In the same breath, however, natural starlight could also be used for the urgently needed deceleration maneuver. As soon as the probe is about 5 stellar radii away from the triple system, it could turn its sail around so that it's slowed down by the light of the stars in front of it. A computer simulation has shown that the braking effect of the light in combination with the gravity of the stars could actually be sufficient to let the probe swing into the system. However, such a process takes time, and the spacecraft would now be on its way for not just 20 years, but a whopping 100. Even more patience would be required if the probe is also to reach Proxima b. In this case, the total flight time is estimated to be as long as 140 years. At this point, however, it's not yet possible to say which adjustments the researchers will make in the future and which variant they will ultimately choose. And it will be a few days before Breakthrough Starshot becomes more than just a bold idea. The scientists involved estimate that the development time alone will take 20 years, and yet it can already be said that the challenges of such a project can be overcome, at least on paper, and that, in the not-too-distant future, humanity may succeed in indirectly leaving its home system and studying exoplanets up close. To study the subscribe button up close, you don't have to leave for Strange Star System. Press the thumbs up and subscribe now to never miss a new video from us again. We'll see you soon.